Okay, well, thank you everybody for coming back, for surviving part 1. Let's see how many we have at the end of part 4. Thank you very much for coming back for the second part. So today is the second lecture. The other two are in 2 weeks. I'm going to talk about two aspects today. I'm going to talk about flagella and the physics of flagellar propulsion, understanding from fluid mechanics principles why is it that flagella are allowing cells, of all types of cells actually, to move. And then we'll talk in detail about basically sperm cells, eukaryotic cells, and I will talk about some of the history of the field of the historic calculations that people have done to be able to predict the speed at which cells move, and then some more recent work about optimization and active filaments. And I'm sure you've seen some of those things about active filaments, at least in Jean-François, some of Jean-François' lectures of the last few years. So first, let's talk about the physics of flagellar propulsion. So last time, I talked to you about two different ways for cells to move in a fluid. One is the way a bacterium swims, and it uses a helical flagellar filament, basically a rigid helix, and it rotates the helix in the fluid. Now, if you look at a schematic representation of that helix, and I like to understand, I like to kind of zoom in on the relationship between the geometry of the filament and how the filament moves relative to the fluid. If I look at that helix, this is a left-handed helix, which rotates. If I look from behind the cell, if this is the cell body, and I look from the back, then they rotate in a counterclockwise fashion, so against the clock the other way. So if I look at two pieces of this helix, imagine I look at the point which is in the foreground next to us, and this is a part of the filament which has a positive slope, and that filament instantaneously moves down because the helix rotates counterclockwise, so it rotates like this. And in contrast, the part of the filament that is locally aligned with the negative slope, the part that is in the background, that part is instantaneously going up. So I have the relationship between geometry, so the slopes, and the instantaneous motion. So you're either having a positive slope, you go down, or negative slope, you go up. Now, if you look at a sperm cell, should just be the next slide. Why is it not working? There we go. So if you look at the next type of motion we discussed for a sperm cell, this is a traveling wave of deformation. This is no longer a passive rotation. This is now active deformation of a flagellar wave. And if you look in this case at the motion of material points, let's consider what the wave looks like at some time t1. So this is my first sine wave at t1. And then I'm drawing the shape at a small instant later in time t2, just above t1. So now the shape, of course, there's a traveling wave, so the shape, it appears as if the shape has been displaced to the right because the traveling wave is moving to the right. But of course, the material points are not moving to the right. They're moving up and down, just with some interesting phase, distribution of phase along the filament. So if I look at, and if I want to kind of understand in which direction the filaments are moving, whether the material points on this wave are moving up or down, I just need to look at the difference between the initial shape and the shape that is drawn just slightly later in time. So clearly what I can see is that the points where the filament was going down are moving up, because now those points are being located right here. They're being translated up. And the points where the slope was going up are moved down. Okay, if I take any point right here, then it is now moved here. So again, it's the same relationship between geometry and kinematics, both for prokaryotes, rotation of helical filaments, and eukaryotic active flexible flagella. I have either a slope that is going down and the filament is moving up, or the slope is going up and the filament is moving down. And of course, those two are the same. They're just a mirror image. There's just take the first one and then you flip it, do a mirror image, and you get the second one. So actually, those two things are the same. So there's something about the physics of taking a slender filament and moving it at some weird angle relative to its geometry that leads to propulsion. So we're going to try to spend a few minutes trying to understand from fluid mechanics why that's the case. So last time I told you that if I have a cell or an organism that moves in a fluid at very low Reynolds number, the fluid flow around it satisfies the incompressible Stokes equation. This is the equation for fluid mechanics, mechanical equilibrium in the fluid for a Newtonian fluid. And I can calculate instantaneously forces and torques or moments that are applied to the cell, okay, as integral of the stress. And the stress is the sum of the pressure, the isotropic part, plus all the stress that has to do with the shear and the viscous part. Now, what's interesting about this is that those equations are linear in the boundary conditions. We talked about this last time. We talked about this issue of having the equation of motion being linear. So if the velocity and the pressure are linear in u and omega, That means that the stress is also linear in u and omega, which means that the force and the torque have to be linear in also u and omega. So all these things are going to be instantaneously linear in u and omega. So therefore, if I give you two vectors, vector of size 3u, vector of size 3 omega, and I want to get a vector of size 3f, a vector of size 3t, the torque, and those two are linear, that means that linearly related to one another. That means that I can write, in general, the force and the torque instantaneously. There is some big matrix which relates it to u and omega. It looks like there's a bit of a resonance in the sound, but I don't know why. So relationship, the instantaneous relationship is linear between basically all the dynamics and all the kinematics. And in the middle, we call this the resistance matrix. And we're putting a minus sign outside of it for obvious reasons I'll explain in a second. This is a resistance matrix. So this is a 6 by 6 matrix. There are three components, so it's a 6 by 6 matrix. And it turns out that matrix is symmetric. So you can show that you can use a principle, something in continuum mechanics on the principle of virtual work, where you consider different types of motion and how they're coupled through the intrinsic symmetries of the equation. And you can show that as a result, this matrix has to be symmetric. This is called the principle of virtual work. Okay, something that is classical in continuum mechanics. Now, I told you last time that I had a kind of instantaneous relationship between the work done by anything moving in a fluid and the viscous dissipation. And it turns out that this means, so last time when we talked about energetics, we said that, well, the application of energetics of last time to this motion is that minus F torque dotted by u and omega turns out has to be positive. This is the dissipation in the fluid. So this is the rate of working of anything moving in a fluid that experiencing force and torques that moves with speed u and rotation rate omega. It turns out with a minus sign that goes into the dissipation. That's always energy gone. So the consequence of this, and this is why we put a minus sign, is that this whole thing, if I put a minus sign on side of it, so I cancel the minus sign, that matrix not only is symmetric, but all of its eigenvalues are strictly positive. Okay? So that means that there's another consequence, which is R is positive. Because it's symmetric, I can diagonalize it. It has 6 eigenvalues, and those eigenvalues are all strictly positive. Right. Another thing that's interesting for you to know is that R, basically, if you write it as A, B, B transpose, and D, it has to be B transpose for this thing to be symmetric. So you cut your 6 by 6 matrix into different 3 by 3 matrices. Then they have known scalings. Each of them have known scalings. There's something interesting with the viscosity mu and the length. Okay, and in particular, what we know is that A scales linearly with u and length. Okay, it scales linearly with u because it's a force and a torque, which is therefore it's a stress. And the stress scales with the viscosity or the pressure, but the pressure also scales with the viscosity, so everything scales with the viscosity. Okay? And from dimensional analysis, you can get that it's one length scale. And you can also get that B scales with mu times the square of a length, and then D scales with mu and the cube of a length. And so what you will see often written in books is that actually R, you will write it as mu times a length scale with some new matrix A, length scale square with some new matrix B, let's call it A tilde and B tilde, L square B tilde transpose, and L cube D tilde. And those matrices tilde depend on essentially nothing that has dimensions. They don't depend on the viscosity. They don't depend on the length. The only thing that they could depend on is the geometry and the shape. So that means that your A tilde, B tilde, and your D tilde only depend on the shape. Okay, so for example, for a sphere, we know what A tilde is. It's 6 pi. If we take for L the radius of the sphere, then it's just 6 pi. That one is 8 pi. and B is 0 for a sphere. And if the object is chiral, we'll talk about this for bacteria, then this is non-zero, and there's a coupling between rotation and translation. Okay, so this is true for any body. Now, flagella are not any shaped body, they're slender filaments, they're slender bodies. So if I have a body that is elongated, then I can simplify this a little bit further. I can say, let me consider the filament in an intrinsic frame of reference that is some sort of symmetry axis of the filament. So if I have to take my slender filament, okay, I'm going to call T the axis, T as in tangent, the axis along the elongated axis of the filament. I'm going to call N1 and N2 the two normals, 2T. Okay, so of course I can take any axis I want, X, Y, Z, but it makes sense to use this because those are the principal axes of symmetry of my shape, and the hydrodynamics problem in that frame becomes much, much simpler. In that case, if I just focus on the relationship between force and velocity, my A tilde in that frame, in my T, N1, N2 frame, or axis, then becomes diagonal. Because then by symmetry, if I take an elongated shape and I pull on it, then I will get only a force in that direction. I won't get nothing in the perpendicular direction, and that's the same for all the symmetry directions. So for those three directions, I get that A tilde is diagonal. So I can write A tilde as alpha, beta 1, beta 2, and then the rest is 0. So in that frame, that intrinsic frame that is moving with the filament everywhere, okay, later on we'll make that frame move when the filament is not straight, then my matrix here is diagonal. Not only that, if the filament is smooth, say, for example, it's axisymmetric, so the shape is like a tube, then of course there's no difference between N1 and N2. They're the same shape, and so therefore your beta 1 and your beta 2 should be the same. Those two should be the same, let's call it beta. Okay, so simple enough, just using symmetries and geometry. Yes?
Are you talking about the local frame of reference and local matrix, or are you considering?
At the moment, I'm talking about a shape that is like this piece of chalk. At the moment, the shape is not allowed to vary. It's just literally this. So that in that case, it's not really local. It's the same at every point. Later on, we'll talk about moving it. Okay, so now we want to, because we had to write this as a matrix, it's not particularly nice. And in applied math, people like to write things in a compact way. And there's a nice compact way to write this, is to write this tensor. So now my tensor A tilde, there's a way to write this matrix in a notation that uses tensor notation. So I'm going to write this as alpha TT. So the TT tensor is a tensor that is 0 everywhere, except it has one component in the T entry on the x-axis and one on the y-axis. Okay, so that's the tensor 1 and then 0 everywhere else. Plus beta N1, N1, plus beta N2, N2. Now you can write this a little bit simpler by noting that the identity tensor, so my tensor, which is simply 1, 1, 1, some people who write it in book write it delta or identity, it doesn't matter. Then of course this is just the tensor with 1, 1, 1 on the diagonal, so this is T, T, plus N1, N1, plus N2, N2. And so that means that your matrix on top, you can rewrite it in this very nice compact way. This is the one that you will see in books about flagella. It will be written as alpha TT. And then, if you factor out the beta, what you're left is N1, N1 plus N2, N2 tensor, which is nothing else than identity minus TT, right? Because you can see that's this bit of the identity. So therefore, what you're left with is plus beta identity minus TT. Okay, so this is the notation. This is a standard notation, intrinsic notation for the resistance matrix for slender filaments. Now, what do I need to do about, so if I take this piece of chalk and it moves in a fluid, that means that in terms of the relationship between the motion of the piece of chalk and the force, all I need to know are those two values, the value of alpha and the value of beta. If I actually give you a formula, if we derive a formula together for this, then we can characterize the entire mobility or resistance of this thing. Okay, so I'm going to show you a movie. So it turns out that beta is always larger than alpha. Every time the shape is elongated, It's equal to alpha when the shape is a sphere. And then as soon as you start elongating it, even just a little bit, you take a sphere, you squish it a little bit so that there's one more direction that is elongated and one that is shorter, then that beta is always above. And in the limit where it's basically exponentially slender, the ratio is 2. So let's look at this. So this is a movie from G.I. Taylor, taken from the same movie that I used last time. In that movie, what he does is he takes two identical rods, and they're the same weight, so the force that is applied to them is the same, and he's going to measure, he's going to illustrate the speed. Now, here in this problem, the force is fixed, and you're measuring the speed, so you're comparing alpha and beta. Really, you're comparing 1 over alpha and 1 over beta, because since the force is fixed, the speed in the tangential direction will be the force divided by alpha, and the other one will be the force divided by beta. So you're comparing the inverse. So they're the same weight, same force, and he's dropping them at the tip of them, the bottom point, most bottom point of both of them is at the same place, and then we see what happens. It's going to take 10 seconds. And clearly what we see is that the one that is elongated goes faster. So there is less resistance in that case. Yeah. So if there's less resistance, the inverse of alpha is larger than the inverse of beta, and so therefore beta is larger than alpha. Okay, it's about twice. You see, if you look at the very tip, the very end of this, it has approximately moved two marks, approximately, roughly speaking, whereas the other one has moved only 1. So that ratio of 2, roughly speaking, you can see it just by doing this. You can do this at home with a viscous fluid, the same experiment. Okay, so what's the value of alpha and what's the value of beta? So to calculate this, then it becomes more complicated. Then it's more than what I can do in a few minutes. To do this calculation, we have to really learn how to do hydrodynamics at low Reynolds number. You have to take a course. So in Cambridge, this is what we teach in our 4th year course in fluids. To think about this kind of in the simplest fashion is to imagine, okay, well, suppose I have a filament. This is my rod, and it's moving along its elongated direction t. Then what I know is that my rod is going to, as it's being pulled, it's pushing on the fluid at every point. So locally, the force, there's kind of distributed amount of force that is exerted by the rod on the fluid that it's moving. So one simplest way to do this calculation, therefore, to estimate the value of alpha, is to say, well, let's imagine that I zoom in, and I have an individual force that is exerting, well, forcing on the fluid locally. What is the flow that it creates everywhere? And then what I'm going to do is I'm just going to add up those. And because it is a continuum rod, then I need to do an integral to actually do this calculation. I'll get the result. So the force due to a point force is well known. It's called a Stokes let, after Mr. Stokes. And if you have a force F, which is a vector with dimensions of a force, then the flow is given by the Green's function of the Stokes flow. So a u at a position x, let me write it this. This is perhaps very formal, but it's nice to write it like this. The flow at a position x for a force which is at a position x prime, another position, is given by, there's a linear relationship. It's linear because we're still solving a linear Stokes equation. And that kernel is called the Ozin kernel, which is the solution to basically forcing your Stokes equation with a singular point. Okay, so that kernel right here, G is a tensor. So G of R being the distance now between the point where you're applying the force and where you're measuring it, is 1 over 8 pi mu identity of R plus the tensor RR of R cube. Okay, so R here just means the absolute value of my direction vector. This is an exact solution. We know this exactly. So we know that if we apply a force somewhere, we create a flow, and that flow decays like 1 over r. It decays very slowly with space. Okay, this is one of the important features of this. This has a 1 over r decay in space. So what does that say about, therefore, the total flow? Well, the total flow is going to be given like some integral. So if I measure a point, a velocity now on the rod at some position x, so let me call x this position, I'd like to figure out the speed that is exerted by the sum of all those forces that are distributed on the filament. Then I need to add up those forces I need to do an integral of a flow that has this magnitude, so it's on the order of, ignoring the prefactors, it has a magnitude of about 1 over mu times 1 over distance. And I may have to integrate this over the filament x prime, the location where the forces are. So if I integrate over 1 over r, then this is going to give me a log, because I'm integrating 1 over distance, some of it to the left, some of this to the right. And so I'm going to get something which is on the order of 1 over mu, and then I'm going to get a log of what? Well, a log of 2-length scale, a ratio of 2-length scale. One is where I end the integration, and the maximum point where I end the integration is something on the order of the length of the filament. So that's L, the length of the filament. And then, of course, this will diverge because this is a singular contribution. So I need to cut off that integration to a local point, and that local point is cut off by the only other relevant length scale, which is the typical cross-section of the filament. So if I go back to my filament, and I give you length scale, and I call this, I have multiple yellow pieces of chalk today. This is now the first one I break today. So if I call the order of, typical order of magnitude of the cross-section or the diameter or the radius, doesn't matter, A, and the typical length L, then this has to be of that order, of the order of L over A. We know that that has to be something like this. And obviously, I have forces, so I have uniform distribution of forces F, so F, and that's my solution. So that means that alpha and beta both have to be, and I can do the same in the perpendicular direction because I can replace my forces that are horizontal by perpendicular forces. Alpha and beta both have to scale like mu over ln of L over A. Okay, this is the basis of something I will mention in a minute. Now, the last thing I want to tell you, so that's, we know that those two had to have dimensions of mu. Okay, by the way, I've reabsorbed the viscosity dependence on alpha and beta. Okay, I remember I had taken it out of a matrix, but it's standard to actually put that back in. So that's why I have the viscosity. If you still want to have the viscosity out of the matrix, you just replace this mu by 1 in your integration. Now, the last thing I want to discuss is that I haven't told you here the difference in prefactor. Remember, we've shown experimentally that beta is always above alpha. Where in that calculation does that appear? Well, it appears in the fact that this tensor is anisotropic. So if you look carefully at this tensor, if you zoom in and imagine you put a force, F, at the origin, and you calculate the flow that is exerted on a circle of equidistant from the location where you applied the force, well, if I'm right here and imagine that I right here create a flow of speed v, in front of the force, I'm going to create a flow of speed 2v. Okay, and the reason for that is this term. So this term is isotropic. This term gives me the same value anywhere on the circle, but that term gives me 0 contribution on the line perpendicular, and it gives me a contribution of 1 on the line that is aligned. Okay, this is the anisotropic, intrinsic anisotropic response of Stokes flow. So the factor of 2 is embedded in this tensor. It's all in this tensor. And when you do a line of force that is aligned with the force, then you get the contribution of the 2. When you do the line of force that is perpendicular, you get a contribution of 1. And so that means that you get beta over alpha is approximately 2. Okay, so if you do all the calculation correctly and all the prefactors, you're going to get something like alpha is approximately 2 pi mu over ln of L over A, and beta is approximately 4 pi mu over ln of L over A. Okay, and there are a lot of work that was done in the 60s, 70s, and 80s to make better and better and better approximation of those equations. But the most important in physics is how they depend on the parameter, which I've illustrated, and with the difference in value, well, the difference in value when they're very, very slender is exactly the difference of 2. Okay, so that's what I had. Yes? All good? Okay, so now what happens, and that's the question you asked me a few minutes ago, when the filament is not a rod anymore, when it's an actually distributed filament. So this is also work, classical work in hydrodynamics, and after that will be done, by the way, with hydrodynamics. We'll go back to biophysics. This is classical work from the 70s, is to try to understand how to go from rods to filaments. And so this is classical work called either resistive force theory, or if you want to be more fancy, you call it slender body theory. So there's a way to mathematically, kind of in a very systematic way, go from one to the other. So now I'm looking at this filament. This filament is deforming, okay? And it has, now my tangent vector is obviously changing with the filament. It was dashed at some time in the past. Now it's solid, so there has been some local velocity of the filament relative to the background fluid. And I would like to calculate the force. Well, it turns out, so this classical work tells us two things. One, if the filament is slender, so that this L over A is actually a very large number. How large is a very difficult question to answer to get mathematically correct. Okay, these are people do PhDs just try to understand how large, what how large mean. And B, if the filament is only gently curved, okay, so if I call the curvature typical order magnitude of the maximum curvature times the length of the filament, that's dimensionless, then I want this to be maximum order 1. Okay, so I'm not allowing a filament to be a loop that loops back on itself. I want this to be, you know, like a sine wave, say, of order 1, where the amplitude is about the wavelength. If you do this, and you can absorb papers that are 50 pages long and you enjoy going through the algebra, then you can show that you can extend this relationship that I wrote right here. You can extend this, let's say star, to locally to filaments. So it's the same physics, except now it's a local relationship. You now interpret this as a local relationship when T is the local tangent. Now, of course, the meaning of T is no longer that of a rod with one vector. It's a different T along the filament because this vector T is different. So the way it's done in the literature and written is I'm going to call F. This one is going to be a vector. It's the force per unit length. So it's the force density that is exerted on the filament. And that is going to be, with the right notation, we're going to call this minus sign from the resistance matrix. I put it right here. And I'm going to have two coefficients dotted with U, and U is the local filament velocity relative to the background fluid, and if the fluid is moving, that means that U will be the difference between the motion of the filament and the flow. So if you have a flow in the background, that's where it goes. And then I just need to use this tensor. Now we use different notation. In the case of filaments, we call this C parallel TT. This is my parallel drag coefficient plus C perpendicular 1 minus TT. Okay, that have the same meaning as your alpha and beta, it's just different notation. And the important thing in this formula, so this is a very important formula historically, the important thing is now T is now a function of S, the arc length. So if I call S the arc length of the filament, so if my filament is written like this and I call S measure from S equals 0 on one end all the way to S equals L, then T is a function of S. So this has to be understood as a local relationship. At the point S, this is a given tensor, but of course that tensor varies as I move along the filament and relates locally U of S with F of S. Okay, and I have distribution of stuff, and if I want to integrate to get moments, to get forces or moments, then I need to do integration. Okay, that makes sense? Right. Okay, so if I go back to this, then you can use this. We can use this formula to show mathematically that if you integrate, so I'm not going to do the math because I think I've done enough math for today, but you can basically go back to this formula and show that your filament that is moving up is going to generate, so if you were to apply this formula and calculate the component in X, I was planning to do it, but I think I should skip it. I'm just going to give you the result. Imagine now I have this filament. Okay, this filament is going to be oriented with some angle theta relative to the horizontal. So I'm going to count theta positive, the sign positive of theta in this direction. This one is a sign negative. So theta is the angle between this x-axis and that part of the filament. And I calculate, as I move along the y direction, perpendicular, I'm going to calculate the amount of force that I generate at right angle with the motion, exactly right angle, so the x component. So that formula is the difference, you can show it's the difference between the drag coefficient. So this is, by the way, just homework. You just show this in homework. It's linearly proportional in u, and it's linearly proportional in the sine of theta times the cosine of theta. So obviously, if theta is 0, then the force is 0, then I go back to my isotropic case where I move the filament up and I just have a vertical force. If the angle is pi over 2, if I move up, I also just get a vertical force. But anything in between, I generate a force that is perpendicular to the motion. See? It's actually proportional to the sine of twice the angle. So now let's look at what that formula tells us. Remember, C perpendicular minus C parallel is the same thing as beta minus alpha. This is a positive number. And so let's look at those two shapes. These are the two relationships between geometry and motion that we saw from biology. Well, in this case, u is positive, but the sine of theta is negative, which means that I'm generating a proportion to the left. This one, of course, is simply the mirror image. So the u is negative, the sine theta is positive, which means that my f is also negative. So both cases give me proportion to the left. So therefore, this is the physics of locomotion. Okay, this is the physics of locomotion. If I look at for my helical proportion for a bacterium, every point along the helix, the relationship between the local geometry and the motion of this geometry creates a proportion that goes to the left. Now, on a helix, every single point is the same by helical geometry, which means that as I'm rotating my helix, I'm generating a force on the helix. In other words, the helix is experiencing a force due to the fact that it's rotating that is at every single point located to the left. So those drag forces are not interfering, but they actually add constructively with one another to all push the flagellar filament to the left. It's exactly, therefore, the same for a eukaryotic cell. The only difference is that for a helix, every point on the helix is the same at every other point on the helix. So the amount of force that I'm generating is the same at every point. For a wave, it's not quite the same because some parts of the wave undergo large displacement, like right here in the middle, but then some parts of the wave undergo zero displacement. So there's a modulation of the amount of displacement that I get. Therefore, there's a modulation of the force, but only of the magnitude. The direction is still pointing at every single point to the left, but it's just that sometimes it's very small and sometimes it's very large. So it's intuitively, we already see that this is kind of less optimal, because if we figure out the best way to generate propulsion from the fluid, then we would like to take advantage of it the same way everywhere on the filament. So intuitively, it makes sense to think of this type of motion as more efficient, because this one is a little bit wasted. Oh, here I have zero propulsion, here I have zero propulsion. Okay, so this is the interpretation, the fundamental interpretation of propulsion for a fluid using a flagellar filament or a flagella, and it's the same physics. You know that it's important that it's the same physics for bacteria and that it is for eukaryotes. And I hope you, for those of you who don't know a lot of hydrodynamics, I hope there are people like this in the room, then this was interesting and worth learning to get there. Okay? Yeah? Okay. All right. So now, let's apply some of these things to think about eukaryotes and how eukaryotes swim. So I told you last time, if I zoom in, if I do a cross-section of the flagellum of a sperm cell, then I get a structure which is akin to muscle and muscle fibers. Not quite, but it's kind of similar in spirit, where I have filaments which are moving relative to one another, sliding relative to one another, and generate bending waves. And we also looked at that movie. Actually, we already looked at that movie today. So here's the fundamental question. That question came about in the 50s, although only one person worked on this really in the 50s, and it's in the 70s that this field exploded. Is the simplest question: how fast does this cell swim? Like if I give you this movie, in the frame of the cell, I'm not telling you how fast the cell is swimming. I'm just telling you this is the frame rate of my camera. This is the geometry. Please predict to me how fast the cell is moving, and then let's compare it to what we see in the lab. So that question, the first person to ask this question was G.I. Taylor, who was kind of the most influential fluid mechanician that ever lived in Cambridge. So we like to claim him as one of our own in Cambridge. And he was talking to people in zoology who basically posed this question to him, and he did not believe it was possible for anything to move in a fluid without inertia. So remember, I wrote the Stokes equation. The Stokes equation are the equation of fluid mechanics where you throw away everything that has to do with inertia, because you're on such a small length scale. Initially, as he told other people, he thought, well, what I'm going to get is a very small speed because I have a very small amount of inertia, thinking, well, if I actually kill totally inertia, I'm not going to get zero, right? So he said, I need to convince myself. So he did this calculation for a sperm cell that is a two-dimensional sperm. It's basically kind of a waving magic carpet that moves in a Stokes flow. And he wanted to know, is it possible for this to move totally with zero inertia? Or do you get small amount of motion just because you have small amount of inertia? Is it a continuous limit or not? And so he did this calculation. You can do this calculation. We teach this. Now it takes about 30 minutes to do this correctly on the board. Do this limit in the long wavelength limit. And the answer is, yes, it works, even with zero inertia. You do get swimming. And if you have a wave that propagates to the right, the swimming is always to the left. And that swimming, if you non-dimensionalize, if you relate this to the wave speed, it's actually quadratic in the amplitude. Okay? So it's a minus, this is a classical minus a half result, times the square of the dimensionless amplitude. So number one, locomotion is indeed possible with an inertia. It's not just because you have a small amount of inertia that you have a small speed. With zero, totally mathematically zero inertia, you get motion. The speed is quadratic in the amplitude of the wave. This is now a classical result that has been seen in many other contexts. And the locomotion, and that's something also we see a lot. Actually, you asked me a question about this last time. For simple, smooth shapes, the locomotion is in direction opposite to the wave. So you're sending a wave of propagation in one direction, and you're moving in the other direction. So this was a fake sperm cell. This is a two-dimensional sheet, and it was a long wavelength, but it would be nice to be able to actually solve for this for a real cell. So Lighthill, who was another very influential fluid mechanician, he worked on everything in fluid mechanics, from meteorology to turbulence to noise to turbulence, and then he also worked on cells. He wrote one of the most influential papers in that topic. He asked the question, well, can I do a calculation that is better than a simple waving sheet? Can I actually do real cell calculation? So there's one beautiful calculation he did in his book, which I'm going to highlight to you for a few minutes. He said, well, imagine I have a sperm now. It's a flagellar filament. It's a deforming flagellum. I'm going to assume that it deforms exactly like a pure traveling wave. Can I use the fact that it's an exact traveling wave to get the information? So imagine, so I'm going to write down the wavelength of this wave, lambda. Okay, so the wave number is k. The frequency is omega. So the speed of the wave to the right is going to be omega over k. And I would like to calculate the value of u. So what are the steps I need to do? Well, before I do anything, what does dimensional analysis tell us? The speed will depend on two things. Well, because all of the hydrodynamics is governed by those two drag coefficients, C parallel and C perpendicular, they have to come in somehow. Then it will be a function of the frequency of the wave, of the wavelength or the wave number, and then something that has to do with the shape, because with these 4 parameters given, that's not enough. Is it a sine wave? Is it a square wave? What is it? So if you use dimensional analysis, you can of course convince yourself very easily that U over C, the ratio between the swimming speed and the wave speed, can only be a function of two things. One is the ratio between the two drag coefficients. They both have the viscosity in it. That's the only thing that has units of the units within the viscosity, and so therefore they can only appear as ratio. So I'm going to call rho the ratio of the drag coefficient. And the other thing that's left is the shape. No other dependence on anything that has dimensions. Okay, so I need to find a function of the drag coefficient ratio and the shape that gives me this. So it's a very simple shape, a very simple function if you think about it already. We went from a function of 5 variables to a function of 1, plus somehow the shape has to come in.
Omega goes away because you average over time?
Well, if it's a finite size filament, and you average over time, and this way you convince yourself that omega goes away. In Lighthill's calculation, imagine this to be an infinite filament, and if it's infinite, then it cannot depend on time. Yes, either one. So to do this calculation, we have to use resistive force theory or standard body theory. The force density that exerted from the fluid is related, this is what I wrote on the board, to the u, which is the local velocity of the filament relative to the fluid. Now, to do this calculation, I need to find u. So Lighthill has a very elegant way in his book to figure out u. He said, well, okay, this pointer doesn't work. So what are the body kinematics? How does the body exactly deform? I'm going to use the fact that it's a traveling wave to get an exact equation for the deformation of the body. So this is what the body looks like. I defined to you already the wave speed, the wavelength, I'm going to call big lambda the wavelength measured not along the axis of the wave, but along the actually material points on the filament. And so it's a larger wavelength. Okay, it's a larger one. I just measure from a top, go down and up, and I measure the total length of the filament along this. Whereas lambda is just a projection along x. Okay, so the first thing to do is to say, well, I'm in the, so if I go back, sorry, this keeps clicking twice. So the first thing to do is I'm going to do the calculation in the frame of the lab, where the fluid at infinity doesn't move. In that frame, the cell is swimming to the left with some unknown speed u. So the first thing I'm going to do is I'm going to jump into that frame. So I'm going to jump in the frame, so the cell is moving to the left. I'm going to jump in the frame that moves with the cell. If in that frame, the fluid moving this way, the fluid, therefore, at infinity appears to be moving in the other direction with the same speed. So therefore, in that frame, so in the swimming frame, the condition at infinity is u along the x direction to the right. That's the first thing. Now, the second thing is I'm now sitting on, say, the cell body, but on that frame that is swimming, I'm looking, but I can still see a wave going away from me. Because remember, there's a wave that is traveling in the body frame. So what I'm going to do now is I'm going to jump to another frame. I was in the swimming frame, and now I'm going to jump in the wave frame. So I'm going to move with the wave. Now, if I move with the wave moves to the right with speed c. So if I go into that frame, that means that the speed now at infinity, I have to subtract that speed, so it becomes u minus c. But the beauty about going into that wave is that if I look around me, nothing is moving. Because I'm sitting with the wave, and I'm just being displaced with the wave. Say I'm sitting at the top of a sine wave, then around me the shape is not changing anymore. The shape is not changing, but the material points are moving. Because remember, in the swimming frame, the material points only go up and down and up and down. So now if I move to the right with the wave, the material points have to somehow find a way to go to the left. But because the shape is changing, the only way they can do this is if they move tangentially along the shape. Okay, so that means the material points, I'm moving like this in the wave frame, and the material points moving backwards relative to me locally, tangentially at every point. If they were not moving tangentially, I would detect a change in the shape. Therefore, that's the only way they can do it. So that means that in that frame, now I know everything about the deformation. In that frame, the motion is minus the tangent. If I call t the unit tangent vector, then the motion is in the minus t direction. Now, how much exactly is it moving in the minus t direction? Well, you can calculate this exactly. Why? Because for the time that it takes for you to move one wavelength lambda along x, material points have to move backwards exactly minus big lambda along the filament. They have to do more journey. You're moving along x, but the material points are going up, are going down, and going up, and going down. So they're going faster than you exactly by that amount, which is the ratio between big lambda and minus lambda. So that means that I know exactly what u is in that final frame. It's exactly minus the traveling wave speed times the ratio between big lambda and little lambda. And if I know the shape, I know the value of this. Just measure it. So this was in that frame that has a flow that goes to u minus c at infinity, which means that now I can go back to the lab frame by just subtracting that flow at infinity, and I know exactly, therefore, back in the lab frame what the speed is. The first bit is the change in frames that I had to do, and the second one is the motion of the material point backwards relative to the traveling wave. And in that equation, what's beautiful is that I know almost everything. I know little lambda, because I can measure this. I know big lambda. This is also just a function of the geometry. T, my tangent unit vector, is also just geometry. It varies, but I know how it varies if I know the shape. C is the wave speed. Measure the wave speed. I also know c here, so I know everything. Ex is just the unit vector along x. And the only thing I don't know is u, is this swimming speed, the magnitude of the swimming speed. And how do I find u? Well, I find u, I need one equation to find one unknown, and it's such that the force, the total force for the free swimming cell is 0. So therefore, I calculate from resistive force theory my x component of the force. I'm going to integrate it to find 0, and therefore, that will give me one equation for one unknown. And that's just integration. The rest is just algebra, just plugging in and then enjoy some algebra, and then voila, here's the answer.
And that doesn't assume that the slope is small or anything?
Doesn't assume that the slope is small or anything. I'll talk about this in 1 minute. Correct. Purely nonlinear geometrically. Correct. The only thing that it assumes is that you know exactly how to relate the forces from the fluid to the deformation through this tensor. So you can do this calculation. It's homework. It's not so long. That one is not particularly painful. It's almost enjoyable. And you get this result. OK, there's a delay between the click and OK. So here's the result. This is the classical result. So if you do the integration, you get the ratio between the swimming speed and the traveling wave speed. There's this formula. But that formula only has two things in it. The first one is rho. Remember, I define rho as the ratio of drag coefficient. It's about a half. So there's a rho here and there's a rho there. And then there's a beta. That beta is the only parameter of the geometry. Okay, remember I told you we were going to get a function of rho in shape. Well, it is a function of rho in shape, and the only shape that comes in is a beta. And beta, if you call the waveform, if you define the waveform as x of s, the arc length, and y of s, that is 1 over the length over the integral of the square of x prime. And really what it is the mean value of the square of the cosine of the waveform. So if you measure geometrically, if you characterize geometrically the waveform with theta, of course theta varies with s, with the arc length, but of course theta, the mean value of the cosine is simply the ratio between the x wavelength and the total wavelength, and the mean value of the cosine square is a number that is less than 1, but it doesn't have a clear geometrical interpretation beyond that integral. Okay, it's the mean cosine square. And that's the function of the shape. And that's it. That's the only thing that matters. Everything else goes away from this calculation. Okay, it's a beautiful, beautiful calculation, but you don't have to assume anything beyond this standard body theory type approach. Now, if you now want to say, well, I know how to do the calculation in the long wavelength limit, okay, as you mentioned, then you can do this in the long wavelength limit, and you can show that it agrees exactly with the result from Nightingale. By the way, important things to note from this formula. First of all, that number is always positive. So because I've defined u to the left and c to the right, locomotion is always in the direction opposite to the wave. Number two, if you put in numbers, knowing what we know for rho and the typical value of beta for a sperm cell, you get that this ratio is about 20 to 30%, depending on the cell. So you get it in the lab frame, it's less than 1. So in the lab frame, you will still observe a wave moving to the right and the cell moving to the left. Okay, because the cell moving to the left is not strong enough to compensate for the wave moving to the right. It's about 20, 30%. And of course, the last thing that is very important is that there is this prefactor 1 minus rho. The anisotropy of the drag, the fact that we shown that beta was above alpha by about a factor of 2, that is totally crucial for locomotion. Because if beta was alpha, then my drag coefficients would have a rho of 1, and if rho is 1, then that number is 0 and it doesn't move. So you can only move because if you have a filament, the drag is not the same this way and that way. That's the only reason why it's possible to move. And by the way, if you use a complex fluid that has different friction, then you can play with this rho. If you, for example, imagine having solid friction at a different rho, imagine moving in a granular medium, imagine moving in a viscoelastic fluid. So there's a lot of studies that have figured out the impact of the fluid environment on the drag.
And what fixed the velocity of the traveling waves?
Well, in this calculation, I'm taking it to be given. So in this calculation, I'm taking a movie from my experimentalist friend. They're giving me the value of c, and then I do the calculation. Now, this is a kind of almost biophysics, I guess, which I guess is appropriate for this lecture. But this is much more difficult for me to answer, because the origin is, you need to select a frequency, and you need to select a wavelength. And there's been a lot of studies trying to understand kind of and Jean-François has worked on this, and Jacques Pro has worked on this, and Frank Ulicker, trying to understand the self-organization at the molecular level that gives rise to the kind of the spontaneous appearance of traveling waves. And I'm not going to talk about this really too much.
There's also the fact that your filament is infinite and in real life,
Right, so I'm going to talk about, this is what I'm going to talk about in a minute, yes. So this calculation is very idealized because the filament being infinite, it has infinite resistance to motion like this. It has infinite resistance to motion like this. So actually it just moves in one day, like this is the idealized version. But this is what applied mathematicians like to do, which is to make simpler and simpler and simpler and simpler until it's doable. And then people will make it more complex later. Now, if you do it for finite size filaments, it's more complex. Now, if I have a finite size filament and I have a traveling wave, imagine I have an instantaneous traveling wave moving along the axis of the filament, then the first part of the kinematic of the motion is the same. So this is what we had before. This is the kind of change in frame coordinate, and this is the motion. I call this q, but that's, remember, this was the tangential motion. This is the same. But now I have more degrees of freedom. My cell could also, in addition to moving along its axis of the wave could also move instantaneously in the axis perpendicular, but also could rotate. So I need to add 2 more degrees of freedom, 1 additional degree of freedom in translation, some perpendicular motion perpendicular to the wave direction, and also a rotation in the 3rd direction. And that's just for planar wave, by the way. I could also have 3-dimensional waves, and then it becomes even more complicated. So I have 3 degrees of freedom, so I need 3 equations. I need a second force balance equation, so the forces have to balance along the wave axis and also perpendicular. And I also need to balance moments or torques so that the cell remains free of force and free of torque for all time. So that becomes much more complicated. It's hard to get beyond long wavelength. It's hard to do anything by hand. You can do it numerically, and then you can compare with experiments, and it works wonderfully. So this is an experiment. I chose this one. This is from the group of Frank Uliker, 2010, where they've done experiments with bull spermatozoa, and they compare with the predictions from the theory. The theory is basically what I just told you, just made it in 3D, so that it has 2 degrees of freedom in translation and 1 in rotation. So this is why there are 3 plots. Instantaneous parallel motion along the long axis of the cell body, perpendicular and rotation rate. And in red are the prediction from the theory. So, and the black are the experiments. And you can see very nice agreement. Now, it's much nicer for U perpendicular and omega than it is for U parallel. And that's because that is the motion in the perpendicular direction averages to 0, but has high amplitude. It's what we call the order epsilon problem. It scales with the amplitude of the motion. So if you actually do mathematical calculation, calculate this will scale like the amplitude of the wave. And same thing with omega. It averages to 0, but the amplitude around that 0 is proportional to A. This is a higher order problem, and this is a square problem. You can see the amplitude is smaller, and this is quadratic in the amplitude, and there's more noise. I mean, it still is able to follow somewhat what the experiments are doing, but obviously the agreement is much nicer in these 2 directions. The other thing you can do, and I took this from a very nice annual review of fluid mechanics paper from the Oxford group, is to do real complicated 3-dimensional computations to actually generate the flow, the total flow that is generated by the cell. So these are experiments on the left for human sperm cell in low viscosity fluid, in high viscosity fluid. If you change the fluid, you're going to change the forces, the resistance from the environment, and that feeds back on the cell, and so the waveform is different. And they did some computation to try to compute what instantaneously the velocity field look like. So this is an example where you basically taken at the same instant of time. And you can see a kind of very different distribution of flow speed around the cell. In this case, for this particular waveform compared to that one, where there is almost no motion in the first half of the flagellum, and there's very high amplitude motion at the distal end, whereas here it's a kind of a traveling wave of deformation that also occurs right here. The other thing to think about, and that's something that I'm sure Jean-François has talked in his lectures a lot, is this issue of activity. So many of the problems that applied mathematicians work on are the simpler version of the problem. In fact, it is related to the question you just asked, where I'm being given the shape and its deformation, and I want to solve for the external flow, not thinking about what exactly generates the force. But of course, in real life, you have this filament is active, and the hydrodynamics and the kind of fluid resistance and the drag balance some passive elastic resistance. The filament doesn't want to be bent from a passive point of view, so if you bend it, it will resist and wants to bounce back, but also some internal activity, and that's the activity that is responsible for the motion in the first place. And so there's a large literature on the fluid dynamics of active filaments, starting from the 60s. Here's an example of, again, from I believe it's also for the group of Frank Uliker, we're comparing the active filament model for experiment, also for bull sperm cells, and the prediction from theory. And this is, I just wrote down an equation, not really deriving it. This is the long wavelength version of an active filament. It has all the essence of what you need. It assumes that the resistance is only from the outside fluid, which is a bit of a controversy. In fact, Jean-François worked on models recently where the resistance was assumed to be mostly from inside the filament, and the sliding motion from inside the filament. So here, my resistance is from the outside. This is where my dissipation takes place. It balances instantaneously with bending, passive bending, and internal activity. So there's a question to ask, an interesting question, which is to say, well, if I look at the shape, is the shape mostly balancing instantaneously the drag, or is the shape mostly balancing the bending? And that's captured by a dimensionless number called now the sperm number. So if I compare the order of magnitude of this term with that term, they're both scaling linearly with y. So all that matters are going to be length scales coming from the fourth derivative and time scale coming from the frequency. So that's this dimensionless number, which is c perpendicular L to the 4 omega over b. So that's something like a fourth power of a length divided by something else that has dimensions of a fourth power of a length. So if I take the fourth root of this, I can define a dimensionless number. And that's the sperm number, so it's just taking a 1/4 of that, which is a length divided by another length scale. And that length scale is a length scale where hydrodynamics and bending exactly balance, where they're about the same order of magnitude. This is called the LS2 hydrodynamic penetration length. And a simple way to do this, to figure out what that length scale is, imagine you take a filament, an elastic filament in a viscous fluid, and you just oscillate it up and down on a given frequency. Well, after a while, the deformation will be 0. And so deformation will be confined to some length scale, where the drag that you get from moving balances the elasticity. And the order of magnitude of that length scale is that length scale L omega. It depends on the frequency, depends on the drag or the viscosity, and depends on the bending rigidity. And for sperm cells, it turns out the sperm number is much, much, much larger than 1. So that ratio is much larger than 1. So it's mostly the balance for those organisms is between the internal activity and the drag. The sperm number, if you go and calculate the intrinsic penetration length in those cases where bull sperm, it's on the order of a few microns, and the length of the cell, big L, is multiple tens of microns, and so that ratio is much larger than 1. And if you take it to the power of 4, it's even stronger. And so there are a lot of studies that look at, which one of those two terms balance. For cilia, it turns out sperm number is much smaller, and so the balance is really three-way balance. And there are other cases that looked at in internal dissipation in the fluid inside the filament, for example. So it's 59, so perhaps I should stop here. I think that's good. That's a good point to start. And then in 2 weeks, I will talk about bacteria on the Monday, I think.